I'll try to not spend too much time on the slides, but really dig into the code and the development aspects of this topic. All right, so first let me start with a real-world scenario. Before I talk more about StreamInsight and about the cloud service that is offering StreamInsight in Windows Azure and StreamInsight itself, if necessary, I want to start with a very real, tangible user scenario that motivates a lot of the aspects and features that I'm going to talk about later. What you see here is a dashboard that gives insight into the user experience during the streaming of a keynote at a conference. In this particular case, it was the Mix conference last year. And what you see is a recent dashboard that shows how the streaming is working for people in terms of buffering and session duration. So what this provides is an insight into the customer experience, basically, for that video streaming use case. What happened here is, if you look at the graphs, the average buffering at some point is going up and the session duration is going down. There's a direct correlation. The stream started to not work well anymore. The streaming clients, the Silverlight client in this case, people are watching through Silverlight clients. The clients started to buffer, and people got frustrated, eventually, dropped off the feeds, so the session duration basically dropped off as well. And this is a display that was updated every few seconds, every 30 seconds, I think. So it's really the real-time insight into what's happening into the content distribution. Why did this happen? The keynote happened on the first Tuesday in a month. I don't remember which month, March probably. And as you know, what happens on the first Tuesday every month is Patch Tuesday. So that was unfortunate, but there was some interaction with the content distribution network, and machines were patched automatically. Long story short, the video distribution and streaming didn't really work, at least for some users. And what happened then is somebody saw this on this dashboard, and instead of having to analyze the problems after the fact, after the streaming is over, when you can't really do anything anymore for these users, the problem was recognized right away, and then measures could be taken to improve that experience while it is going on. To make that, it's only affecting a small group of people and only for a short period of time. So what I wanted to demonstrate here is the value of real-time insight into scenarios where I have telemetry data that I can process. The important aspect here is that the clients that provided the user experience, the Silverlight video players in the user's browsers, were instrumented with means to send telemetry events to a central service. Telemetry events about the user experience, like buffering, session duration, and interactions with the player, so that I can react on these events. I can aggregate them in real time, and then have a human consumer of that dashboard act upon issues. So just to motivate the whole use case and set of scenarios of event-driven processing of streaming telemetry data, and being able to act on that in as close to real time as possible. So that was one scenario. I want to touch upon a few other scenarios where an infrastructure that allows you to do such processing and aggregation of telemetry data from distributed sources comes into play as well. Typical example that we always bring up, infrastructure monitoring. So the goal here is to monitor large-scale cloud infrastructures, services in real time by grouping and aggregating performance counters, for instance, over temporal windows. Such analytics can be offered to the cloud customers as the service themselves. And part of this scenario is a spectrum of latency behaviors where a low latency monitoring experience can be offered, for instance, as a premium service, besides a default offering with higher latency. That could be one possible differentiation to provide such insights to the customers of a cloud infrastructure. The point is that aggregations over such different window periods can be run in parallel at all times, right? As a user, I shouldn't have to worry where do my insights into the telemetry come from. I should just be able to pick and choose what's the granularity of information and how often it's supposed to be updated. So that's kind of the gist of it. Here, the sources, the stream producing sources are machines, are a cluster, a compute fabric that I want to monitor. For instance, to handle peak loads, load spikes, to ensure the SLA for the customer is fulfilled. Second one, and this is basically what I just talked about in the previous slide, the real-time monitoring of user experiences when consuming certain content, like in that example, streaming media. So that could be a video telemetry scenario or other kinds of consuming a user experience on a client and then on many distributed clients, all of which I need to collect telemetry from and then aggregate in a central place. Another very related and very typical scenario is web analytics, clickstream analytics from web browsers. Again, this is about processing, analyzing, and reacting to the customer experience of a website, say a web store where I want to do recommendation queries based on the existing user interactions in terms of clicks and search keywords to be able to serve ads or just the navigational structure of the website. Again, what we have in common here is widely distributed sources, a high number of sources, potentially hundreds of thousands or millions of clients using their web browsers, and the necessity to collect and process these click streams in a central place so that I can aggregate over all of them in an event-driven fashion, in a near real-time fashion with low latency, and then being able to react on user behaviors on certain issues and situations, again, as close to real-time as possible. And lastly, we are also targeting vehicle telemetry scenarios where here, naturally, the sources are cars, connected cars, which more and more cars are already being able to send diagnostic data or GPS location data to some central service where I can then try to recognize certain issues, certain patterns, to pattern matching over the diagnostic data events, or aggregate GPS data from a fleet or from a set of cars, and then reason about that. For instance, recognize certain traffic conditions and scenarios based on the complete set of GPS location data that I got within a certain time frame. Again, being able to react on these in real time. That's the target scenario. All right, so this is all about event processing. So far, I didn't really talk about where is the processing actually happening. What is the product that does it? What's the infrastructure? What's the deployment? What's the compute fabric here? I will mention StreamInsight as a product, and I don't know how many of you know it. In a few slides, I want to introduce StreamInsight itself as the Microsoft event processing platform that is released as an on-premise product. And what I wanted to do here now is to motivate why would we use the cloud for these scenarios, for these types of processing of streaming event data. And we see two, I would say, categories of scenarios that justify this effort, justify a service in the cloud. First of all, the event data might already be in the cloud, like the clickstream analysis, right? I have web browsers going against web servers. The web servers are in the cloud. That might be the Microsoft Azure cloud or something else, but the machine-born data, the generated data, is already not really an on-premise generated data. So I'm already in the cloud with the data. In another set of scenarios, the event data might not be generated in the clouds, but it is already globally distributed. For instance, the connected car scenario, where I have cars that produce data that are geographically distributed, or weather sensors, or aggregating over plant floor data of multiple plants, multiple sites within a geographic area. So the data I want to aggregate across these geographically distributed sources is already has to travel over the network, whether it's traveling to a central cloud service to be processed or to an on-premise deployment. Doesn't really make a difference for the data sources, right? So what both of these have in common is the data is not local, right? And that justifies our paradigm here. What we want to convey is bring the processing to the data, not the data to the processing. And beyond that, of course, there are the typical cloud benefits. Typical benefits of running a service, not having to maintain a data center, reduce total cost of ownership, being able to scale out more or less elastically, right? Provision more compute resources for a certain use case in a comparably short period of time, maybe even elastically adapting to current throughput of data, right, without a human interaction. And then lastly, being able to use a service instead of having to maintain an infrastructure.